So in first 100 seconds universe evolved to this particular stage. 10 is for 2 seconds. So all that is very complicated, probably very difficult to explain it in words without using mathematics or equations. But so you can see here that all fundamental interactions such as gravitation, as Professor Rajwali referred, electrostatic interaction, electromagnetic interaction, weak interaction, all of them are confined here in these first 2 stages. In the third stage, the deconfinement started, and then from here the universe became very transparent. Then it started expanding very fast, and here your baryonic method came up. Your antiproton, antineutron, all these antiparticles, they all started evolving. And so this first 100 seconds, actually most of our physical objects which we see around, which we all are composed of, they came up. And so our family universe and our family physical laws all evolved during first 100 seconds of what we call first 3 minutes. Then here actually it was the matter-dominated era where the large-scale structures started forming, and galaxies came up, stars came up, and all large-scale structures were almost on the verge of completion of their construction. Then the universe once again became transparent. It was another transition era up to first billion years. From here, right now we are here, the present universe, our universe is almost 15 billion years old, and its average temperature is 3 degrees Kelvin. Okay, so these are some familiar equations Professor Rajwali has also talked about, and Einstein in his famous equation of the universe introduced this lambda term which represents cosmological constant. Sometime later he said introducing this lambda term of the cosmological constant in my equation was a blunder. But once again, when apprised by Edwin Hubble that the universe is expanding and there is a binding or compelling proof of it, there is experimental evidence that the universe is expanding, Einstein probably once again said that there is some importance of this lambda term of the cosmological constant in his field equation. And then he said, what does this lambda do? When the universe is expanding, now let's construct a story. Universe was born at one point of time, say Big Bang. It started evolving, it's still expanding, then what happens? Okay, it will keep on expanding. Until when? It will keep on expanding at some critical stage, and we anticipate that there will be a critical point which is something we call anticlimax. There is counterpart of the Big Bang, we call it the crunch. The universe once again will fall back, it will contract, and it will collapse into one singular point of very high density. Okay, so that's an anticipated story. What about the physical evidences? So here's the physical evidence, probably. This lambda term signifies that. But how? So when the universe expands, the voids in the universe, they also expand. So as I talked about, universe is nothing but voids, voids and voids. Empty space, and empty space. What is empty space? Any distance, any space, any region between two stars or two galaxies, what is that? It's vacuum. It's almost absence of matter, absence of anything else. That is vacuum. So that when the universe expands, the vacuum also expands. When that vacuum expands, negative pressure develops. And we expect that at some point of time that negative pressure will catch hold of the expanding universe. It will once again be responsible for contraction of the universe. The universe will contract at some point of time that we call the big crunch. How? We'll discuss these nitty-gritties in 2 minutes. So here is this rotor which Professor Rajwali referred as vacuum energy density. So let's call it vacuum energy density. So what is vacuum? First we'll go into that, what is vacuum, and then we'll discuss this vacuum energy density in turn will be responsible for this lambda term, which is of this magnitude as of now, which is a very small quantity. There is point followed by 55 zeros and then 1. I mean, for common man, common sense, it is just a term which can be jumped. But it is not so insignificant. As the universe expands, and it will keep on expanding, someday this term will not be insignificant, this will be very significant, this will be responsible for the contraction of the universe. How? Okay, so here is an interesting image. So we just have some fairy tales. So from the theory of Einstein, just because Stephen Hawking said, or just because Stephen Weinberg said something, that we have a fancy story and we believe it. No. Now we are living in the era of precision experiments. In early 90s of the last century, I think from 91 to 93, an experiment was conducted by NASA called Cosmic Microwave Radiation Background Experiment. And that predicted that the universe is comprising of something like 70% dark energy and all other features which I discussed earlier. That schematic chart which I had shown, released by Fermi National Accelerator Laboratory, is almost a result of that experiment. Then in the first 3 years of first decade of this millennium, another experiment was conducted by NASA, and that is known as WMAP experiment, as it featured in the title of my talk. WMAP is, W is for Wilkinson, M is for Morris, and anisotropy probe. Wilkinson, Morris, anisotropy probe. So here, there is a 360-degree radiation pattern of the universe embedded in just one film or one screenshot. So here you can see the universe at large looks like the same everywhere. And that is something which mathematically Professor Rajbali expressed homogeneous and isotropic. Homogeneous means more or less made of similar constituents. And isotropic means rotationally invariant, that you look at any point in the space, it looks similar. So if you move your telescope in 360 degrees, the distribution and intense distribution of the matter and energy is almost the same in 360 degrees. Okay, so I mean, this radiation map of the universe is confirmed by WMAP experiment. How the experiment works? So here is the probe, and this shield always protects very high intensity radiations to disturb the experiment from disturbing the experiment, and I mean the nearest star sun is the most disturbing element. So the shield is always facing the sun, and then there is antenna on the other side which actually collects radiation from all the angles, I mean in 3 pi sector. Okay, so this is how the radiation data was collected for almost 3 years, and that was analyzed, and that was reconfirmation of the experimental results of the earlier experiment of NASA, that is Kobe experiment. So what is this dark energy now? So dark energy is nothing but the variance in the vacuum energy density of the universe, the jargon which Professor Rajbali uttered and I also talked about earlier. But what is that? So as the universe expands, the voids in the interstellar and the intergalactic medium, they also expand. Thus the vacuum today is not the same as vacuum what it was 5 billion years ago or 10 billion years ago or 15 billion years ago. So vacuum is also continuously changing, the intergalactic or the interstellar vacuum. So how does it change? And what is that source of dark energy? So there are two prominent candidates of the idea of dark energy. One is zero-point energy of the harmonic oscillators, that's how it was applied. Other is virtual particles that mediate the fundamental interactions. They could be source of dark energy. I'll talk about it, or if there is any other candidate for such a hypothesis, we do not know. But let's talk about first and second in little detail. So second part, first. Okay, so first, here is that idea of negative pressure. So that Leibniz term in the Einstein's equation. So that is what is the idea. Okay. The second part, the virtual particles. So actually anything in this universe is an interaction with some other object. You have two fundamental particles. In case of two fundamental particles, they always keep on interacting. It's very difficult to have fundamental particles in isolation, not interacting with anything else. You can help, but for a very short while. So we explain it like this: an electron is coming like this, another electron is coming from other direction. They interact with each other at a certain distance, and then they move away. Okay, and it keeps on happening. So let's think of our interaction. We humans also keep on interacting with each other. I am interacting with you in terms of some verbal discourse. Okay. Another interesting example could be, you can think of Sania Mirza playing with Serena Williams. An observer in the helicopter would always wonder that what is there which keeps these two sports persons at a certain distance. It is the exchange of ball. So either it is the exchange of words, which we call interaction, or it is exchange of energy. And as we learned from our first principles of thermodynamics, that any two objects in this world, in this universe, they always keep on exchanging their energy. They try to be in thermal equilibrium with each other. They keep on exchanging heat. They keep on exchanging their energy. They keep on exchanging their momentum. And they try to be in equilibrium with every other thing in the surrounding. Is that okay? So, in the same manner, every object, right from a fundamental particle to any object at large scale of distance, is in some interaction with some other object. And that interaction could be exchange of energy, that could be exchange of momentum, and that could be exchange of something else. That can be exchange of electrical charge, if it is applicable to. So that's how these fundamental particles interact with each other. But this interaction is by means of some virtual particles. In this particular case, when electron is interacting with another electron, this exchange is that of photon. This is where some people suspect that these virtual particles responsible for that interaction, probably they could be the source of that vacuum energy density. Okay, then let's formally define what is vacuum. Generally when we talk about vacuum, we say or we think of nothing. Okay, vacuum is not nothing. It is something. But what is that? So let's use some negative approach also. So it is absence of matter, fine, that could be. It is absence of matter. If there is no matter, fine, there could be some energy also, trapped energy. Then void, a space that is empty of matter, fine. Next, a space relatively empty of matter, fine. And last point, a space in which the pressure is significantly lower than the atmospheric pressure, fine. Okay, let's once again realize the order of magnitude of the pressure that persists around us. Okay, I will not go into these details. Let's try to understand the magnitude of the pressure that persists around us. Okay, so in a typical vacuum cleaner, the pressure that is created is of the order of 1600 torr. In liquid ring vacuum pump, it's of the order of 1 to 0.1 torr. Smaller is the magnitude of pressure, greater is the magnitude of the vacuum. Okay, so rotary pump, it's 1 torr or 10 raised to the power minus 3 torr. I mean, it's a full range. Incandescent bulbs, which we see around probably now, they are the species going on extinction. They will be replaced by CFL now, I think LEDs very soon. So in a vacuum tube, a picture tube of television and all that, the vacuum is of the order of 10 raised to the power minus 7 to 10 raised to the power minus 10 torr. Near Earth outer space, it is of the order of 10 raised to the power minus 6 torr. Pressure on the moon, it is of the order of 10 raised to the power minus 11 torr. Once again confirmed experimentally. And lastly, the interstellar space, we expect it should be of the order of 10 raised to the power minus 17 torr. Torr is Newton per meter square. Okay, so you would ask, how do you know? I don't know. We expect, scientists generally expect, I mean, they have a strong sense of feeling or strong feeling of magnitudes of physical quantities, probably they know better. So we expect that it should be of the order of 10 to the minus 17 tau. Okay, and here is an interesting anecdote or recall from the pages of history, and that's where you realize the power of vacuum. So just to make you realize that vacuum is not nothing. Because when we think of vacuum, we think this it's nothing. Vacuum is absence of matter, absence of anything else, and so it's nothing. Vacuum is not nothing. Then what is it? So it was, I think, in the year, in 1500 something, let me recall the year. It was 1654. So a scientist called von Guericke in Germany, he did a very interesting experiment, and what he did is he took two identical hemispheres of iron with small, very, very smooth edges, just connected to them, planted a valve over there, sucked the air out of it, and you can imagine, I mean, we didn't have the rotary pump and the diffusion pump in those days, and so you can imagine how strong the vacuum must have been. That must have not been all that strong vacuum as we can do it today. We can achieve vacuum of the order of 10 to the minus 11 ton these days in the laboratory. But in those days it was not possible. But whatever order of magnitude he could achieve, he did this experiment. He did join the two hemispheres of iron ball, which was hollow, but he didn't join by means of your nuts and bolts. He didn't guide them either. He just kept a ball over it, sucked air from that hemisphere, that sphere, and created some kind of vacuum inside that. And then it was a tug of war situation. There were two teams comprising of first hit, and this is the consequence. Firstly, he did the experiment with 20 people on each side, and there was a tug of war. They could not separate the two hemispheres of that iron ball, which was not joined by any soldering material or any kind of nuts and bolts. And still they couldn't separate it. Just one last minute. Then what he did is he employed 16 horses on each side. 16 horses, a team comprising of 16 horses on this side and 16 horses on that side. And then there was a tug of war, and that even team of 32 horses could not separate the two hemispheres, not joined by any glowing material or not joined by any kind of nuts and bolts. So that was the power of vacuum, and then the lean and thin fellow came, and then he just released the air from the wall, and the two hemispheres separated from each other. So that's the power of vacuum. Okay, thank you very much. Probably I could be some giving on. And then Guericke did this experiment once again in front of Reichstag, where the Emperor of Germany used to live. And then once again he did this experiment third time in the town of Magdeburg, probably the town where he was mayor of that town. I mean, he was a scientist, but at the same time he was mayor of that town. And he did the same experiment, and 16 horses on one side and 16 horses on the other side. They could not separate. Then that lean thin fellow went in front of everyone and then released the air from that sphere, and the two hemispheres separated. So that's the power of vacuum. So we believe that power of vacuum will catch hold of the expanding universe one day. The universe once again will start contracting, and someday there will be a big crunch. Thank you very much.
And we have used two terms, matter dominated era and radiation dominated era. Actually, initial stage of the universe was supposed to be radiation dominated era. Radiation rho, matter density is 3 times pressure, that is called matter. And the present universe is present matter dominated era, where pressure is 0. That's the Biyani model as I described there. The Biyani used matter dominated era. Thank you. Namaste. My name is Masano Miyata from Jaipur, Japan. The topic of my presentation is the exploration of ilmenite-based thermolytic materials. This is the content of my presentation. Firstly, research background and my research materials and experimental results and calculation results and conclusion. This is an overview of industrial primary energy. The industrial primary energy, only 34% is used like this. Meanwhile, that of 66% represents a huge unused energy resource available worldwide. This is the temperature profile of industrial waste heat. The waste heat below 150 degrees accounts for a large percentage. So, some technology that can regenerate that waste heat into available energy is necessary. So, we focus on thermolytic conversion. Thermolytic effect enables direct conversion from thermal energy into electric energy. This is a schematic picture of the principle of direct effect. The temperature difference of the module like this generates the electric motive force by direct effect. We can evaluate the thermolytic performance by using figure of merit according to this formula. Rho is electrical resistivity, S is thermal power, kappa is thermal conductivity, K is absolute temperature. The good thermolytic material means low electrical resistivity and low thermal conductivity and high thermal power. The tellurium compounds such as bismuth telluride or lead telluride are well known as thermolytic materials like this. The tellurium-free thermolytic materials are required because telluride is rare. So we focus sulfide thermolytic materials because sulfide is cheap, abundant, and non-toxic. Recently, reported sulfide thermolytic materials tetrahedrite show the high heat value shows. So we explore the new thermolytic materials. Especially, we focused on sulfide material ilmenite. This picture is the crystal structure of ilmenite. Chemical formula is nickel, antimony, and sulfur. So, including 3D transition metal as nickel. The crystal structure system is cubic, so it is high symmetric crystal structure. This study investigated the thermolytic properties of ilmenite and their substitution system, E-X, TRX, SBS, experimentally and theoretically. This is a sample synthesis. This is a condition of sample synthesis. The mixture of stoichiometric elements was sealed in evacuated closed tube ample like this. And for material material, sun power S and thermal conductivity were measured by two-probe method in PBMS TTO. This is the temperature dependence of electrical resistivity for ilmenite and their substitution system. This line is material material, this line is iron substitution system, this line is cobalt substitution system. The law for all samples increase linearly with increasing temperature that show metallic behavior. The residual resistivity, which is constant value low at low temperature, increases with TR substitution like this.
The neutral electricity rate is dominant at low temperature. The law is linear to T like this, which indicates that acoustic scattering is dominant at high temperature. This is temperature dependence of some power for ilmenite and their substitution system. This black line is mother material. This line is iron substitution system. This line is cobalt substitution system. The sign of S for nickel 1 X, TRS, SPS change from negative to positive with decreasing temperature like this. Indicates that the whole contribution is dominant in the low temperature region. However, the electron contribution becomes dominant at higher temperature. The sign reversal behavior reflects that the nickel 1 X, TRS, SPS are density function theory, DFT, non-conserving Schur potential and Schur atomic localized edge function. Calculation condition is like this. The electric dispersion relation and density of states and partial density of states are using K grade 11. K grade means the number of grid of K states. The temperature dependence of some power S K grade is 71. The S for ilmenite is calculated from the temperature dependence of chemical potential mu according to this formula. This is the result of calculation, density of states. This is ilmenite, this is cobalt substitution system, this is iron substitution system. Black line is total density of states. Color line is partial density of states. For ilmenite, the density of states for nickel, antimony, and sulfur hybrid orbitals is dominant at Fermi level EF. The EF for nickel 0.75, here 0.25, SPS located in the wide conduction band indicate the system is metallic. This result is consistent with the experimental results. The band edge for TR substitution lifts up and now TR substitution like this. The density of states for nickel, TR, SPS, SP, and S hybrid orbitals near EF is split by TR substitution because like this. There it is. Because the crystal field is changed by the substitution. This is the electric dispersion relation. This is the ilmenite and this is cobalt substitution system. This is iron substitution system. A whole pocket exists near the gamma and R position, which indicates that the ilmenite is multi-carrier system. It is consistent with the experimental results. The bands are split by crystal field with ER substitution, magenta and red band like this. This is a schematic picture in the density of states. The degree of crystal field splitting is different from cobalt substitution and iron substitution like this. Iron substitution is stronger. The TR substitution decreases the slope of density of state compared to ilmenite, which indicates that the absolute value of S decreases with TR substitution according to this formula. It is
now our next speaker, next for the oral presentation is Ms. Parveez Kumari. Please welcome Ms. Parveez Kumari.
consider third influential model with flat potential and massless error field is investigated. To get an inflationary universe, we have considered a flat region in which the potential is constant. To get a deterministic model of the universe, we assume that this relation parameter is constant. We find that spatial volume increase with time representing inflationary scenario. The Hubble parameter decrease with time and the Higgs field evolves slowly but the universe expands. The model representing decelerating and accelerating phase of the universe and isotropic. The result match with certain astronomical observations. Now I came to introduction. The state of exponential extension of the universe is termed as inflation. The inflationary scenario is satisfactory solution to some of conceptual issues in cosmology and is not understood by the standard Big Bang cosmology. The inflationary scenario explains several mysteries of the modern cosmology like homogeneity, the isotropy, flatness of observed universe and the primordial magnetic monopole problem. Booth introduced the concept of inflation while investigating the problem of why we don't see magnetic monopole today. Booth had also suggested that rapid expansion is due to vacuum energy and after inflation the universe is filled with bubbles. The inflationary scenario is also confirmed by CMB observation by Bassett et al. The notion of inflation is one of the best mechanisms at early stage of the universe to explain the flat and homogeneous and isotopic nature of the present day of the universe. The inflationary model, the universe undergoes a phase transition characterized by the evolution of Higgs field. The inflation will take place if potential Wi-Fi has flat region and in this region the phi evolves slowly but the universe expands in an exponential way due to vacuum energy and suggested by Stanford. In this paper we have investigated inflationary cosmological model in constant of transition space-time in potential Wi-Fi and deflation parameters are assumed as constant. We find that Higgs field evolves slowly but the universe expands. The spatial volume increases with time, representing inflationary scenario. The models represent accelerating and decelerating phase of universe with match with present astronomical observations. Metric and field equation. We consider quantitative in orthogonal form is given by equation first. The Einstein field equation is given by equation second. The energy momentum equation is given by equation third. The conservation relation is given by equation 4 and the non-linear differential equation is given by equation 5, 6, 7, 8 and 9. We are interested in the inflationary solution so gravitation is considered. Thus we consider potential is constant. The scale factor for the line element first is given by equation 14 and to find the deterministic model of the universe we assume deflation parameter is constant. And the scale factor is the equation is given by equation 16. The Hubble parameter, the extension theta and the spatial volume are given by the equation 17, 18 and 19 and the scalar field is given by equation 20. Now I came to conclusion. The spatial volume increase with time representing inflationary scenario. The Hubble parameter is initially large but decrease with time. The Higgs field evolves slowly but the universe expands. The model represents decelerating and accelerating phase of the universe is beta greater than 0 and beta less than 0 respectively. And these are references.
Now I would like to invite Swati Singh on the dais for the presentation. Please welcome Swati Singh. Myself Swati. I am doing my research work on the title Locally Rotationally Symmetric Biyani type first massive string cosmological model with vacuum energy density and magnetic field in general. In my research work, I take Biyani type first cosmological model, which is generalization of the FRW model, because FRW model are unstable near the singularity and can't explain the early state of universe. So I take Biyani type first cosmological model. Our Biyani type first cosmological models are anisotropic and homogeneous. This anisotropy is due to presence of string. Here string is topological defect due to phase transition. But Biyani type first cosmological model is anisotropic due to presence of string. So as well as string will disappear, the anisotropy will disappear. In my cosmological model, I investigate my cosmological parameters in presence of magnetic field and the addition of cosmological constant lambda. And the cosmological constant lambda has discussed briefly. Now I will discuss that how magnetic field will affect our cosmological parameters. Now I will discuss my abstract. Biyani type first massive string cosmological model vacuum energy density and magnetic field is investigated. To get the deterministic model of universe, we assume that shear sigma is proportional to expansion theta and as considered by chain and ring, where R is scale factor. We find that energy density, the particle density decreases with time. The vacuum energy density decreases with time, which matches with the astronomical observations. The model in general represents an isotropic space-time due to presence of string. Here I explain that what is string. String is the topological defect due to phase transition. Topological defects mean stable contribution of matter. The value of cosmological parameter decreases due to the presence of magnetic field and model has quantized singularity at t equal to 0. Now I am going to my mathematical work, that how does cosmological parameters will be affected by magnetic field, cosmological constant lambda and other mediums. Metric first is given by equation first. This is Biyani type first metric. Now I apply different conditions on this metric and explain my results. Energy momentum tensor is given by equation second. Tij. This is the distribution of matter. Massive string condition is given by equation 4. Y equals to rho t plus lambda in a co-moving coordinate system given by equation 5. Proportional to expansion theta as considered by Thorne. Thus we write a equals to g to the power n. This is due to shear sigma proportional to expansion theta. Equation 13 and 15 leads to 16. By equation 16, we get cosmological constant lambda equals to alpha b to the power minus 12 plus 1 upon 3, which is the cosmological constant lambda. Here we can see the behavior of the cosmological constant lambda, that how does it behave for the universe. Now equation 16 and 17 leads to 18. By this equation, we get our values. It means we get our matrix. Now equation 20 is the representation of my research work, where T is the cosmic time. Now discussion and conclusion. We find that energy density and string tension density are initially large but decreases with time. The spatial volume increases with time, representing inflationary scenario. The vacuum energy density lambda decreases with time, which matches with astronomical observations. The Hubble parameter is initially large but decreases with time. The model in generally represents an isotropic space-time due to presence of string. The value of cosmological parameters decreases due to the presence of magnetic field. The model has point-type singularity at t equal to 0 given by Matthew. And these are references used in my research work. That's all. Thank you. Piaget, German scientist, gave Bianchi's model, which is capable to describe the early state of universe. It means Big Bang. Now it is not possible to describe the proof of this Bianchi's model here. Okay? Thank you, Swati. Excuse me, ma'am. One more question. Can you please tell me about the Bianchi time inflationary universe and fundamental basis? What is it? The model? Bianchi's model was given by a German scientist, Bianchi, which represents the mathematical representation of universe. Starting with what is universe? Nobody knows. Then Bianchi gives these equations and describes how our universe behaves. So we apply different conditions on this equation and see the behavior of the universe. In my equation is the lambda equals to I described here and A equals to B to the power and sigma proportional to theta, and I get different conditions if you see my representation. If you want to see again, you can see here.
My question was very interesting. What is the mathematical equation of universe? Hello. What is the mathematical equation of universe? Actually, Einstein gave mathematical equation of universe. R I minus half GID plus lambda GID is equal to minus 8 pi PID. PID is fundamental principle. It describes the property of the universe. How he obtained? It was actually I have already given in my first lecture, and you can follow my book or an article. Okay.
Thank you, sir. At the last moment of this session, we pay our heartiest gratitude to our eminent speakers, to Professor Rajpali sir and Professor Alok Pandya sir, who have given us their valuable time today. Once again, thank you so much, sir. And we also give our best wishes to our young researchers for their golden future. So now I would request Professor Manish Biyani sir to kindly present mementos to our Professor Rajpali sir. Please give a big round of applause.